So welcome back to the room with nice AC. Sorry about that. Our next speaker, our next lecturer will be Randy Dumas from quantum design. Some of you might already know that quantum design is a big supplier for measurements for magnetics or spintronics related field research and with a various temperature range. With a magnetic field, strong magnetic fields, very strong, up to several Teslas. Okay. 16 Teslas, okay. Unfortunately, it's too expensive. I cannot afford. So Randy is an application scientist at quantum design, and before that he got his PhD from UC Davis, and he also received his BS bachelor degree in physics from UCSD. And he's an expert in various kinds of characterization techniques, so I probably don't need to spend too much time on that, and Randy will show you like what he knows. Let's welcome Randy.
I'd like to take a picture for my scrapbook. Actually, for LinkedIn, I might post this on LinkedIn. If you don't want to be on LinkedIn, let me know. Like maybe you told somebody you're going to another summer school. That's fine. I won't post it. It's hard to get all of these stuff, but that's a good representative. Sandy LinkedIn. Here. All right. So again, thank you to the organizers for. Can you hear me? Do I need the microphone? I'd rather just have one hand free. Can you hear me? Yeah. We'll see how it goes through the talk. If I need it, we'll use it. So again, thank you to the IEEE Magnetic Society for extending this invitation to me. The first summer school was right around when I was getting my PhD, so I never got to go myself. But I always heard good things about it. So after my PhD, I went to Sweden as a postdoc and then was an assistant professor and had a couple of students I supervised, and they both went to the school, one in Chennai, I believe, and one in Rio. And they both loved it. And I was always like, I was jealous, right? Wanted to come to this in some way. And finally, it's a little bit hyperbole, but it's a dream come true. I'm happy to be here, happy to finally be able to attend. And I learned a lot this morning as well, so I'm looking forward to all the talks. So we're going to be focusing on measurements in magnetism. Broad topic, right? And they gave me no marching orders on what I can talk about, what I can't talk about. So I started by just drawing out a list of things that I could talk about with any sort of authority here. We're already having problems here. Let's see. We're frozen up. We're frozen up already. Boy. We got frozen up. All right, hopefully we're back. See if this remote works. Sometimes there's a problem with this remote. I may have just broke it again. All right, I think we're back. All right, so I started with a list of things that I felt like I could talk about in any sort of capacity, and it was 12 items. We've only got 120 minutes, 10 minutes per topic. There's no way we're going to do that. So we got to make some cuts, and I wanted to make a story for you, right? Just like when you're writing a paper, you got to have a story. You got to have an arc. So there was I spent weeks trying to figure out what kind of art, what kind of story, what subset of these do I want to talk about to give you a general overview of what we do. So here's our outline. I knew that I wanted to talk about vibrating sample magnetometry, and I'm going to group squid magnetometry in here as well. So what are we doing when we're measuring using the VSM? We're measuring the DC magnetic moment, just the length of the moment vector, as a function of temperature or magnetic field. But the DC one, so that was the key that I wanted to hold on to here. So if I wanted to think in terms of measurement frequencies, VSM and SQUID, they're down here at the DC end. As we increase the measurement frequency, let's say, back up here, this is our bread and butter with something like the VSM and the SQUID, right? The hysteresis, the moment is a function of field or temperature, right? The shape of this, the coercivity of this tells us so much. But let's increase the measurement frequency a little bit into the kilohertz or the megahertz range. Now we're in the realm of AC susceptibility. So this is a very important technique for those who study things like spin classes, superparamagnetism, superconductivity, single molecule magnets, etc. It's a technique I actually didn't use much until I joined quantum design. It's not actually so important for most ferromagnetic materials, ironically. Let's go up to the gigahertz range. Let's kick it up a notch. So now we're in the realm of ferromagnetic resonance. We heard a lot about that in the second talk today, right? We saw this equation. I saw this equation on like 50% of the posters earlier today as well. Here we're dealing with coherent precession or ferromagnetic resonance, spin waves, magnetics, etc. Let's go even further to the terahertz regime, ultra-fast dynamics. So this here is just some seminal work, almost 30 years ago already. This, I think, along with things like giant magnetoresistance and perpendicular magnetic anisotropy, is one of the most critical experiments done in the past 30 or 40 years in our field. And it's this rapid demagnetization, which, if I understand correctly, still, they don't understand all the mechanisms here. They've come a long way since the mid-1990s, but it's still an active field of research and has really spurred a lot of things. And here we're studying things, the exchange interactions, energy scales of this length scale here, or time scale rather. But then I looked at this and it's like, well, how do we actually measure this here? What is this measurement? Normalized resonance, what is this? Well, this was measured using a technique called the magneto-optical Kerr effect, or MOKE. Okay, so with MOKE, you can actually get data that looks like this, you can get data that looks like this, and you can get microscopy data. You can get data that looks like this. This is actually some bubble domains where they were studying the DMI interaction in them. When I set out to make this talk, I didn't quite actually fully appreciate just how important MOKE is, right? It's really a versatile technique, spanning DC all the way to picoseconds, etc. But let's say, so this got me also thinking in terms of space now. So with MOKE, round numbers here, submicron type of resolutions. Really, you can only, you're limited by the diffraction limit of light. So if you want to even decrease the spatial sensitivity even more, the resolution to the nanometer realm, you got to do something like magnetic force microscopy, or something that's very interesting these days, and that is scanning NV center microscopy. So this here is going to be our outline for the talk. Sort of the story, it sounds cheesy, I know it, but it's a journey through space and time. That's what I want to give you here. And those of you who have a little bit of OCD, you like things organized, this is a nightmare to look at, right? It's just a bunch of stuff up here. So I want to give you a traditional outline as well. This is what you're used to seeing, things just laid out like this. 6 topics at 120 minutes. Hopefully we can do it. Luckily, a lot of my job was done with the FMR stuff, so I can breeze through that. Thank you. All right, our pedagogical goals for this talk. Realistic stuff. Provide a fundamental understanding of how each technique works without a lot of equations, okay? And you might be like, oh great, he's taking it easy on us. There are no equations. That's totally from me. I can't do math anymore. I don't want to do math. You're going to see some equations. We're going to breeze through them. We want qualitative understanding. I want you to know qualitatively, have it in your heart how each of these techniques work. What are the pros and cons and limitations of each technique? Not every technique can do everything. What kind of samples can you study with a given technique? Ample references, books, publications, YouTube videos. There's so much good YouTube content out there, right? I'm going to upload the PDF of the talk to the shared drive eventually. I haven't done it yet. Most things you'll see, you'll be able to click on it. It will take you to the relevant video or the book or whatever. So hopefully I've taken care of that for you. And again, I'm the guy from an industry, right? So commercial equipment comparisons where relevant. I'm from quantum design. I didn't want to make this talk a commercial. Spoiler alert, it's totally going to be a little bit of a commercial. But you're going to know when it's specific to quantum design, because I'm going to put this Q up here. Then you know it's specific to quantum design. Being a little bit joking there, it's about 50% of the talk. I did try to make it broader than that. Okay? All right, VSM, studying DC AC moment. This is an inductive technique. We're going all the way back to 1959. People used to call this the Foner magnetometer after Simon Foner, this RSI paper that details how a VSM is made. What are the main components here? Primary components are an electromagnet, a mechanism to vibrate a sample, sort of usually a speaker coil could usually be used. Pickup coils in the vicinity of the sample to inductively pick up the dB/dt variations in the field in this vicinity here. We need some electronics to measure the voltage induced in this coil, usually a lock-in or something similar to that. And basically, this is our equation for this system here. Faraday's law, d phi dt, you can go through this if you'd like. At the end of the day, this voltage that we measure here, it's an AC voltage measured with a lock-in, is proportional to some constant, the moment, that's what we're interested in, the amplitude of the vibration, the frequency of the vibration. Of course, we usually throw away this AC term here. We're usually just looking at the magnitude of this voltage here. Then through calibration constants, that magnitude of that voltage is directly proportional to the moment, usually along a given direction. And you can get fancy here. You can pick up coils in orthogonal directions and do vector magnetometry as well. Follow the bouncing ball. All right, quantum design. How do we do a VSM? It's a little different. This here is our flagship PPMS product line known as the Dynacool. So we use superconducting solenoids. They have vertical fields. And that goes inside the cryostat. Our systems are like Swiss Army knives. They're meant to be modular. So we have a motor that we can put on top of here to vibrate the sample. That goes up there. And then we have a puck, specialized puck, that goes inside the system. This is our pickup coil. And then the electronics, basically the lock-in and the thing that drives the motor, exists here in this electronic rack here. So this is our take on the VSM. Let's go into a little bit more details, and it works in our entire family of PPMS product lines here. So we've got a first-order gradiometer. That's just a fancy way of saying we've got a bunch of clockwise windings here and counterclockwise windings here. I only show a single coil in each of these. There's actually many. There's several hundred here in each. Showing the sample vibrating between them, kind of slow so you can see it. Typical amplitudes are on the order of 2 millimeters and a 40 hertz frequency here. We actually take a look at our coil set. We take the protective covering off of it. What do we see? Here's that first-order gradiometer. This is just standard copper wire here. Nothing too fancy going on here. This here is a calibrated Cernox thermometer, so we know as close as possible to the sample what the temperature is. It's very critical in our type of systems. And of course, there's a lock-in amplifier which exists in the electronics bay here. So again, pretty basic stuff. Let's take a look at sort of the field of VSMs out there. I'm going to split this into traditional electromagnet VSMs and quantum design, the superconducting magnet VSM, right? So traditional electromagnet VSMs, the maximum field that you can give with these type of magnets on the order of 3 Tesla or so. And these are heavy magnets. It's much easier to get 2 Tesla. Every little bit of Tesla is just that much more magnet that you need. The power supplies for these things are also enormous as well. But they're also very powerful. With our systems, with the superconducting magnets, we have systems that go 3 Tesla. That would be the little baby PPMS, the VersaLab here. The Dynacool comes in 9, 12, and 14 Tesla. And we also have a 16 Tesla system as well. In terms of sensitivity, that's what you really want to know here. These type of conventional, traditional VSMs, super sensitive. These have come a long way since the VSMs I used when I was a graduate student. We're talking on the order of 15 nano EMU or so at room temperature. I try to put these all on as equal of a footing as possible here. But you will notice that once you start putting variable temperature options inside of these room temperature systems, the sensitivity dramatically decreases. And that's because they have to spread the poles apart, and there's other tricks that they have to play. Similar, when they have their vector options, the sensitivity decreases as well. Our sensitivity, at least at room temperature, doesn't match these. These are far better room temperature. So why would somebody buy a quantum design VSM? Primarily for the easy temperature control and the high magnetic fields. You buy a system like this, if you need that ultra-high sensitivity, again, only at room temperature, let's say you want to rotate the sample. Much easier to do in a system like this. You're studying in-plane anisotropes, out-of-plane anisotropes. Much easier to do here than our systems. Vector capabilities, that's something we don't have. And speed. Electromagnets you can charge very quickly. Those of you who have heard of this first-order reversal curve or fork technique, you can do them much faster here than you can there. You can do them there. We have an option for it, but it will take longer over there. That's the price of doing business when you can go up to 16 Tesla, is you got to slow the magnetic field down or else that magnet will quench. Right? So you have to be very careful. And by the way, feel free to stop me at any time. I keep looking around for a hand or something. And ask questions at any time. All right, now let's sit. There we go. Take it.
Can you please go to the previous slide? Yes. So, what do you mean by vector capabilities there?
Good question. I'm going a little bit quick here. So, normally, let's go back even further. We won't. Basically, let's say in a system like this, normally the magnetic field is pointing along this direction here. Okay? Normally, your detection coils are set up so that you measure the component of the magnetization or moment along the same direction.
Yeah.
But you can imagine putting pickup coils 90 degrees relative to that, and then you can pick up the magnetization component this way.
Perpendicular.
So that's what I mean by vector.
Okay.
So you can pick up
Understood.
usually two components. Let's say you're dealing with something like a thin film. Usually, what are the components you kind of know anyway? So,
Yeah. Okay.
good question.
Thank you.
All right, let's say we want a little bit more sensitivity than these here. Now we're entering the realm of the superconducting quantum interference device, or SQUID. And this is really what people know quantum design for. The SQUID company, that was our first product actually back in 1983 or 4 or so. The first commercial SQUID magnetometer. We're still going to be focusing on the DC moment. It's an inductive technique, but increased sensitivity. So now, same sort of idea. We've got a sample, we've got a gradiometer. It's now a second order gradiometer that's made of superconducting wire. So second order gradiometer has, say, clockwise winding here, counterclockwise windings here, twice as many, and then a clockwise winding here. So the same, we have net number of windings here of 0. There's as many clockwise as counterclockwise, but they're organized in this fashion here. This helps get rid of issues with field uniformity, etc. And I don't show it here, but this is inductively coupled to the SQUID itself, which is a very sensitive magnetic flux to current to voltage transducer. We'll talk a little bit about that on the next slide. But what do we do here is we drag a sample through this coil to this second order gradiometer. At the end of the day, we're measuring a voltage, and we get a voltage waveform that looks something like this here. It's negative here because this is clockwise, it's positive here because this is counterclockwise, and it's negative here because it's counterclockwise. This is this voltage waveform, we call it. We can then fit this using a very simple equation. This is just basic undergraduate level E and M here to then calculate the magnitude of the magnetic moment along this direction, this longitudinal direction here. It's a pretty easy technique. This is actually old data here, how we used to sort of do this here. And that's all we're doing. And we're able to get much more sensitive behavior here because we're using this superconducting quantum interference device, or SQUID. So the complete circuit looks a little bit more like this. Now, we don't have time to go into all these details here, but this here's the second order gradiometer. That's our sample moving inside the gradiometer. And again, it's inductively coupled to the SQUID. And all of this here exists on a chip. The SQUID itself is nothing more than a little chip that we make in a clean room. Dimensions here, roughly 5 by 3 millimeters or so. And again, very sensitive magnetic flux. We induce currents inside the SQUID. And then we basically use this as a feedback mechanism to get a voltage out of this. Unfortunately, we don't have time to go into exactly how a DC SQUID works. If you want to learn more about this, I urge you to take a look at the book chapter here. So actually, myself and another application scientist wrote a book chapter all about how the SQUID works in here. We've got a YouTube video, and this review of Scientific Instruments article also does a great job of explaining how a DC SQUID works. Unfortunately, it takes about 20 minutes to do properly. We just don't have the time for it. All you need to know today is very sensitive flux to current to voltage transducer, and we get a lot more sensitivity out of using a SQUID than a traditional BSN. Commercial SQUID magnetometers, very much just two people in this game. There's Quantum Design and there's Cryogenics Limited. Just kind of curious, who here has a Cryogenics Limited SQUID maybe in their lab back home? You?
No, the lab upstairs has one of them.
Yeah, well, by the way, I didn't ask this before. This is just for ego now. How many of you back in your lab back home have something from Quantum Design? Okay, I mean, it's a significant fraction. So I shouldn't feel so bad about preaching to the choir here. Anyways, you will see some differences between these systems. They like to use third-party electronics here. They're using LabVIEW-based stuff. A lot of the specs are actually fairly similar between the systems. One way in which our system really dominates is we have a different type of detection mode where we combine the best worlds of VSM and SQUID. We call it SQUID VSM. So it's the same detection circuit, same second-order gradiometer, same voltage waveform. Here's our sample. But instead of moving a sample through the gradiometer, we're just going to jiggle it. Okay? So we don't have to worry about most of this waveform. We can throw that away. And all we have to deal with is this little parabolic section right here. Follow the bouncing ball. So again, we've got a parabolic voltage response here. We can go through, we know how removing the sample is a function of time and frequency and with a given amplitude. Go through here, plug this in, use one of those trigonometric identities in the cover of the book, and we can get this type of voltage here. So this is interesting. We're now measuring the voltage not as a function of space, but as a function of time. And we're using a lock-in amplifier to do this. Interestingly, the voltage varies at twice the frequency of the oscillation here. So this is very nice. That means mechanical noise primarily occurs at the fundamental frequency in which you drive something. But we're not looking there. We're looking at the second harmonic. And you can see how that goes here. So if you go through the little experiment here, let's say we move the sample through one physical period. Down, up, down. The voltage goes down, up, down, up, down. So you can see how it varies at twice the frequency. And we take advantage of that. The other interesting thing is that the voltage depends on the amplitude squared of the oscillation. That means we have an enormous dynamic range with the SQUID VSM mode. We can measure all the way from nano EMU levels all the way up to 100 or 1,000 EMU. So that's 10, 11 orders of magnitude in EMUs. And yes, I use the EMU unit system. Ron Goldfarb's not here, so I can totally just use the CGS system. It's what I grew up with. It's what I can do. Feel free to convert on your own. All right, so in terms of sensitivity, the historical view of our system, the old system showed sensitivity on the order of micro EMU. So we've come a long way because now we're dealing with, again, 10 to the minus 8 sort of EMU sensitivities here. And the SQUID VSM mode always beats out the old DC scan mode and has a much larger dynamic range. We can measure all the way up to 100, greater than 100 EMU. It's actually hard to put enough sample in the system to get a moment that large. It's a very powerful technique. It's also very fast. So you can see the red diamonds here. This is the DC scan measurement. So you sort of see the natural scatter here. And then the open symbols are the SQUID VSM mode. So lower noise level and a lot more data. Again, much more powerful. Combining the best of both worlds, VSM and SQUID VSM. Let's compare our systems, right? We've got the SQUID here, the NPMS3, and the VSM. Both of them can use pressure cells. We happen to sell hydrostatic pressure cells. They get you up to 1.3 gigapascals. You can put your own diamond anvil cells in here as well. We have ways to illuminate samples with light, and we have an oven option so you can measure up to 1,000 Kelvin. That's the same between the systems. Where do they start to differ? So again, here, roughly micro EMU level of sensitivities. But you can measure while ramping the temperature and magnetic field, actually quite quickly. So again, good for fast measurements. Here, we get 2 orders of magnitude more sensitivity, but it's best not to measure while ramping the magnetic fields. That's not, you will destroy a lot of the sensitivity. So it can be a little bit slower in that case. But here we actually have a way to rotate our samples in situ. Here we cannot do that. Here we have an ability to actually measure very low coercive samples. Let's say you have a Yig film with coercivity of an earth stick. You basically can't do it in a system like this. A system like this, you can. Other nice thing about this system, we have a special insert so you can measure all the way down to 0.42 Kelvin. It's basically a helium-3 refrigerator. So the moral of the story is you got to buy both, right? If you want to do everything. That's the moral of the story. Joking aside, really it comes down to the sensitivity. If you've got samples with milli-EMU sensitivity, you're dealing with chunks of nanoparticles, large milligram sort of volumes, you might get away with this. You're probably going to measure faster here. If you're dealing with ultra-thin films, those things that are less than a nanometer thick, you might want to use a system like this. It all depends on your sample. If you have very low coercivity samples, this option here is going to be what you're going to want. So again, it all comes down to what your sample is. take a little deviation from techniques and talk a little bit about accuracy considerations. Okay? A lot of people confuse accuracy and precision. Obviously, we want to live here where we have high precision and high accuracy. So precision, I also say, I usually talk in terms of sensitivity, I use them interchangeably, means we have a tight grouping here. Accuracy is how close we are to the bullseye. So this would be a case of high precision, a nice tight grouping, but low accuracy. Generally speaking, painting in broad strokes here, it is up to the equipment manufacturer to guarantee a certain precision or sensitivity. For example, the Squid VSM has a much higher precision than the traditional VSM. But it is primarily up to you, the experimenter, to define how accurate your measurements are. Now, there's ways you can mess up the precision, too, and that's why they hire people like me, application scientists, to look at your data and help you improve these things. But generally speaking, accuracy is up to you, precision is up to us. So I want to talk about 3 sort of case studies here. How accuracy in the reported magnetic field affects things, how the measured moment depends on the sample size and shape. So many people ignore this. It's amazing. And how the background affects the measured magnetic moment. This one most people are aware of. So again, let's go back to our more traditional VSMs and the quantum design systems. So quantum design systems, like the first thing I learned, this is back when I was an undergrad at UC Davis, and I was using the old NPMS. What the lab manager said to me was, hey, that field that is reported in our software, MultiView, many of you are familiar with MultiView, that is not based on a sensor from, like, let's say, a Hall sensor or a Gauss sensor. All that's based on is the current to the magnet. But we're dealing with superconducting magnets, and superconducting magnets are very good at holding on to flux or trapped currents. And therefore, when the system says it's at zero field, it might not be at zero field. I want to talk a little bit more about that now. Now, a traditional VSM usually has an independent Gauss meter or Hall sensor that exists. We can't really see it here, but it's very close to the sample. It's great. You really don't have to worry about magnetic field accuracy in dealing with these types of systems here. Just sort of the way it goes. So a lot of people ask, well, why don't you put a Hall sensor in your system? We don't have room for it. That's bottom line. Or we'd have to put it in a region which varies in temperature. And now we have to have a temperature-dependent calibration of our Hall sensor. These can just be at room temperature, so it's actually a very difficult problem to solve. But I'll show you one way in which we can solve it. But again, let's say this is our superconducting solenoid in cross-section, and we've charged it all the way up to 16 Tesla. We then go to 0 Tesla. Well, we're going to have some trapped flux inside this magnet, which would correspond to having a magnetic moment in the beef of the coil pointing upwards. So that means the stray field from these moments is going to be pointing downward at the sample location. And that's a general thing. When you positively saturate your sample and you come straight to 0 field, you're going to have a small negative remnant field. This is actually data from a MPMS-3, where again, they start off here at 7 Tesla, and this is the field error, come back down to 0. Field error is on the order of 20 Ørsted or so. How does this manifest in a measurement? So this here is a very benign measurement, 10 nanometer thick iron film. And what we show here is we come from the descending branch shown in red, it flips on the positive side. It comes back, and then the ascending branch comes up and it flips on the negative side. And I should also mention that this loop actually went all the way out to plus minus 2 Tesla, which is zoomed in here on the low field response. I still get one of these emails once a month from somebody. They're like, what's going on? Is this new physics? No, this is not new physics. This is instrument artifact that you can totally correct. And I'll show you how we correct this. And it's a natural consequence of this remnant magnetic field. Now in our PPMS product line, let's say you pony up for a 16 Tesla system. The bigger the magnet is, the more room there is for the stray currents to hide. We can get remnant fields of up to a couple hundred Ørsted or so. It's very sizable. And again, we suffer from the same problem, except it would be magnet problem here. So a very easy way we can solve this is simply to measure the palladium reference sample that we provide with all of these systems. You measure this palladium reference sample, which is an ideal paramagnetic sample, using the same sequence that you'll use for your sample, except for the temperature. And we want to measure at 298 Kelvin because we know the susceptibility of the palladium reference sample very good at this temperature. So that's shown here. So, moment versus field, ascending and descending branches. From way out here, it looks okay. It's a straight line. It's a paramagnet. But zooming in, we see hysteresis here. That's not real. That's instrument artifact. And we see the same sort of inverted loop where the descending branch crosses here, the ascending branch crosses here. But we know it should go right through the origin, both of them. So all we need to do is we can calculate the true field by dividing that measured moment by this quantity here, the susceptibility, and we tell you the mass of the palladium reference sample. And again, we know the susceptibility of 298 Kelvin very well. This is just obviously a screenshot from the origin here. And we can calculate the true field based on this measurement of the magnetic moment. Now, all we need to do in post-processing is take this column here and replace it here, and I'll show you how that's done. So this again is our loop with this problem here, this inverted loop, replacing the reported field with the calculated true field, and we get a hysteresis loop that now makes sense again. So this is a very important thing to keep in mind, and it's really only an issue when you need to measure at large fields and small fields. So you can get rid of the magnetic flux in your magnet by first setting a magnetic field of 3 Tesla and oscillating the field back to 0. That'll get you a remnant field on the order of an Ørsted or so. And if I was to measure just between plus minus 100 Ørsted, my loop would look like this. But the second I start to approach half a Tesla or more, that remnant field will come back, and I have to account for that. So it really is only an issue if you need to measure small and large fields. Honestly, why would I measure this all the way out to 2 Tesla? It's clearly saturated, right? Why would I do that? I did it as an example here. All right, sample size and shape considerations. Again, this is the one thing that amazes me that people don't really quite appreciate. So we calibrate our systems at Quantum Design. We use a palladium reference sample, which has these dimensions here. It's a little cylinder. This here is measurements from the NPMS-3. The moment as a function of vibration amplitude shown here in red. This is for that SQUID BSM mode, or the DC scan here. This would be the scan length. So we see that they agree to one another. Notice the scale here, very tight. It's a little bit of scatter here, but it's well within our 1% accuracy specification. But it's this way because we actually calibrated the system to look like this. There are additional calibration things to ensure that this is the case if you have a sample that looks like this. But what is the true moment if the sample size and shape is different than this? So I'll show you what that looks like here. So this here is a sample. It's a piece of erbium YAG. This is an obsolete AC reference sample that we used to use. But clearly it's not a cylinder. And here's the moment as a function of vibration amplitude. Clearly it varies with the vibration amplitude. For the DC scan measurements, it doesn't vary much with the scan length here, but is this accurate? I don't know. We have to see what's going on here. But clearly there's something wrong here. The magnetic moment should not depend on the vibration amplitude. That does not make sense. Well, we provide a little tool for the user where you can put in your material parameters, rectangular prism, the size of this, etc., and we will spit out a correction factor for you. So if we put these correction factors and we correct our data, we can actually turn it into data that looks like this. So again, we've shifted this down. These are now within 1% of each other, and this is a flat line. And this is true also for our PPMS VSM. And we have a similar sort of utility where we can calculate the correction factors for you. This is only valid for cylindrical samples, but honestly, most samples you can approximate. Like a thin film would just be a cylinder that's very squat, things like this. You can play around with it that way. Size and shape considerations are relevant for any inductive magnetometer. So those of you using a more traditional VSM, ideally you want to use calibration samples with the same or similar size and shape as your sample. And you can always go through that Gedanken experiment. Imagine you had a sample which is very large and is vibrating. Well, the moment would be very small because you don't have any changing flux in your gradiometer. Same thing goes if you have very small samples. These things affect things. Now, if you're like me, when I was a graduate student, all of my hysteresis loops, I just normalized plus minus 1. I didn't care, right? And I understand that's most of you as well. But if you actually care, you have to take these things into account. Let's say you're measuring a thin film, and your advisor says, hey, how thick is that thin film? How do you know? Well, you did X-ray reflectivity, you know the thickness, maybe you did some profilometry. He's like, well, let's also do magnetometry. You go ahead and calculate the saturation moment. You divide by the volume. And it's off. Well, maybe it's because your measurements weren't as accurate as they should have been. So these things need to be taken into account. Background considerations. When you make some of the world's most sensitive magnetometers, everything's magnetic. You have to be careful of introducing magnetic impurities. It only takes 4 nanograms of iron to produce a 1 micro EMU signal. Right? With the squid-based system, that's huge, right? So no cutting and handling with ferrous tools. Even diamond scribes can sometimes gall ferromagnetic material onto your sample. If appropriate, make sure to clean with solvents or acid. Obviously, if you have metallic film on a silicon substrate, don't put it in acid. There goes your film, right? So have some common sense here. Everything is magnetic. Diamagnetism, much easier to handle than paramagnetism, right? Diamagnetism is weaker than paramagnetism, and it's basically temperature independent. Paramagnetism you can usually subtract from things, but it does have that pesky 1/T response at low temperatures that you have to sometimes deal with. Ferromagnetism must be avoided at all costs, right? You cannot account for that. So just be wary of that. You put a wafer in your sputtering system on that little platter that you've been sputtering magnetic materials on for the past 50 years, right? Maybe some of that will get on your sample. And again, when you're dealing with very sensitive systems, 10 to the minus 8 EMU sort of signals, everything's magnetic. A very frustrating paper to read from 2009, but it goes through a lot of these different sources of experimental errors. Even handling with ferrous tweezers sometimes can cause magnetic signatures in your sample. So all of these things you need to be very wary of. So background subtraction, the basics. So VSM, the MPMS3, if you're doing the squid VSM mode, a point-by-point subtraction is pretty much all you need. You want to have your moment of your background plus the sample, and you just subtract off the moment of your background. And ideally, you want to have whatever sample holder you have. The only difference between these two measurements is the sample. And usually you can get away with this. But if you're using the DC scan mode for the MPMS3, now you have to be a little bit more careful because we calculate the moment based on that voltage waveform. So you technically need to subtract one waveform from the other and then refit this response. Here's an example of some measurement I did with a very large background. This is that voltage waveform, so position, voltage. Sample plus background, background. Almost no difference between them. So we have to subtract these, and now we finally get something that looks like the response we're expecting. Have to refit this and calculate the moment ourselves. This is a pain. Luckily, we have application notes to help you along with this, and some researchers at Cambridge University came up with a program called Squid Lab, if you have MATLAB, which actually can automate this process for you. So something good to keep in mind for background subtraction. AC susceptibility. Pick it up a notch with frequency. AC moment, again, we're still in the realm of an inductive technique here. Here I show some examples of just DC moments. Paramagnet, diamagnet, superconducting, like the Meissner effect, and then we kill the superconductivity, something ferromagnetic here. Here's an example of a superconducting sample, the DC moment shown in black. So again, this is like this data here. And then as we increase the magnetic field, we kill the superconductivity. To first order, an AC measurement probes the local slope of a DC measurement. So you can see, you can just go through the experiment here. The red data is the AC susceptibility. It's just the slope of the black data here. But because it's an AC technique, we're actually always measuring an amplitude and a phase, or a real and imaginary response. And therefore, we're intrinsically measuring the dynamic response of our sample. So how do we actually do an AC measurement? On the y-axis, I'm going to have the AC magnetic field. We have an AC drop. Usually AC measurements are done at a small or sometimes zero DC magnetic field, or sometimes even a large DC magnetic field. But the thing that's most important is the AC magnetic field. We come in with a known amplitude and frequency, and then we just measure how the magnetization varies in response to that AC field. In general, there's going to be some sort of a phase shift and an amplitude to this response. So if we map this out in the complex plane, we've got an amplitude and a phase, or if you'd rather, we can think in terms of a real and an imaginary component as well. As it turns out, the equipment from quantum design, at least, we naturally measure the real and imaginary components of the AC susceptibility, and then we calculate, through just trigonometry, the amplitude and phase. Most people have an easier time thinking in terms of amplitude and phase, though. So you can see it's fundamentally a very different type of measurement than a DC moment. We're curious how the magnetization or moment vector is now responding to this AC magnetic field. You can go through the thought experiment where you go through a very slow AC field, in which case they'll just follow one another. That's when you're basically just measuring the slope of the DC response. And things get interesting as you go higher in frequency. So just some examples of the spin glass material here. AC susceptibility, the real component as a function of temperature. You get this cusp here, that freezing temperature.